Hi everyone, my name is Christoph. Today I'm going to talk about a gap in the randomized local computation complexity landscape, and it's joint work together with Sebastian and Vasek. So this talk we study so-called local computation algorithms, or short LCAs, and before I formally define them, let me motivate them first. So the fundamental question that we want to understand is what can be computed in sublinear time. And this question is motivated by the era of big data we're living in. So often you're dealing with a really huge input. So think of, as an example about the web graph. And also often the output is huge. So if you want to compute a page rank, you need to compute one value for each node. Hence, it seems if even the output is comparable to the input size, that we cannot really do something meaningful in sublinear time. However, usually we're not really interested in the whole output at once. Hence, the idea that here is that we only want to provide query access to the output. That is, we only want to answer for a given web page whether to return its page rank. And then we can really hope to get something in sublinear time. All right, now let me formally define the local computation algorithms model, or short LCAs. So LCAs are formalism for query algorithms, and they were introduced in the years 2011 and 2012. And LCAs, they provide query access to a solution of a computational problem. In this talk, I'm going to focus on graph problems, and their examples include coloring, MIS, and maximal matching. And for these problems, we want to answer queries of the form, what is the color of a given node U? Is U in the maximal independent set, or is E in the matching? To answer such a query, the algorithm in turn can probe the input graph. That is, it can ask questions, what is the jth neighbor of node I? So here on the right, you can see some graph. And one question one could ask is, what is the second neighbor of the node with ID number 1? And then the answer to this is the node with ID number 3. And then the complexity to measure is the number of probes you need to perform to answer a single query. What I really want to emphasize is that there's no shared state between different queries. In particular, the order of the queries does not matter to the output. In particular, the best way, I guess, to think about it is if you query each node, the output, in parallel, then the algorithm computes some solution, and this solution for all the nodes together needs to be a valid solution. Okay, now let me explain the deterministic and the randomized setting. So in the deterministic setting, we assume that each node is equipped with a unique ID from a polynomial range. However, we will also consider, for the sake of analysis, that the IDs are actually from an exponential range. And then in the randomized setting, what we assume is that each node is equipped with a private stream of random bits, and that the algorithm should succeed with probability at least 1 minus 1 divided by n. Also, we assume that in the randomized setting, there are no IDs. However, this is without loss of generality because we can simply assume that each node uses its first order log n bits to determine its identifiers, and these identifiers are unique with high probability. Okay, so the result that I want to prove today is the following. So let pi be a locally checkable labeling problem. This is a problem, this is a large class of problems, which I'm going to talk about in the next slide. Then if there exists a randomized LCA for this problem pi with a probe complexity of little over square root log n, then there in fact also exists a deterministic LCA for pi with a much faster probe complexity of order log star of n, which one can think about as just being order of 1. Okay, so what are these locally checkable labeling problems that we will study, or short LCLs? They are defined on graphs of maximum degree delta being some constant. And the property that these LCLs have is that the output can be verified locally. What do I mean by that? Well, if the output is correct, so we have some solution, then it's only correct if and only if it looks correct in the R-hop neighborhood around each node, where R denotes the local checkability radius and is just some constant. So what do I mean by that? If the output is incorrect, so let's take coloring as an example. If you don't have a valid coloring, then there exists a monochromatic edge, and hence there exists one node which can detect that by just looking at its one-hop neighborhood that this coloring is not valid. So, and these locally checkable labellings, they include a large class of problems. So coloring, matching, MIS, and so on. Okay, so how are we gonna prove this gap result? So we're actually gonna prove it in 2 steps. So first, we show that the randomized LCA with problem complexity little of square log n implies a deterministic LCA, so we de-randomize it with a much larger problem complexity, but still sublinear in n. And this deterministic LCA actually also works with IDs from an exponential range. And that it works with an exponential range, this is important in the second step, where we then show that we can turn this deterministic LCA into a much faster deterministic LCA with a probe complexity of order log star of n. And so in this talk, I'm actually just going to focus on the first arrow. And I want to just say that the proof heavily uses ideas from Chang, Kopelowitz, and Petty. And later, we're going to see how we can extend these ideas to obtain a omega log n lower bound for the so-called Lovász local lemma. Okay, so what we're going to want to show is that we start with a randomized LCA with probe complexity little over square log n, and we want to de-randomize this LCA. So how can we do this? Well, we basically do 2 steps. So first, we increase the success probability of the randomized algorithm. And how can we do that? Well, we can simply tell the algorithm that the graph has big N many nodes instead of small n. Hence, the success probability of the algorithm increases from 1 minus 1 divided by small n to 1 minus 1 divided by big N. And then as a second step, we argue that we can fix the randomness deterministically in advance, such that with this fixed randomness, the algorithm actually works on all possible input graphs. And this we will do by union bound over all input graphs. We will show that that we can fix the randomness in such a way. Okay, now let me explain this idea in more detail. So in the deterministic setting, I told you that each node, we assume that it's equipped with a unique ID. And in the randomized setting, each node has access to a private stream of bits. Now we want to use this randomized algorithm as a subroutine, and hence we kind of need to go from the deterministic setting to the randomized setting. And this we're going to do by considering some function ρ. And what ρ does is it takes as an input an ID and maps it to a stream of bits. So just consider some arbitrary function that maps IDs to stream of bits. Now what we can do is we can define an algorithm, a ρ of small n. And what it does is it first applies ρ to each ID. And then instead of each node having an identifier, we end up with each node having having a stream of bits. And now with this stream of bits at each node, we can now simulate the randomized algorithm, but now we tell it that the algorithm has big N many nodes, where big N is just a function of small n. And now what we want to show is that there exists some function ρ, some fixed function, such that a ρ of n succeeds on all n-node ID labeled graphs. Okay, so one way to visualize what I have explained is in a 2-dimensional table. So here each row corresponds to some algorithm, so to some deterministic algorithm, which is determined by this function, ρ of I. And each column in this graph corresponds to one possible input graph. And now we can mark a cell green if the corresponding deterministic algorithm succeeds on the corresponding input graph. And otherwise, we're going to mark a cell in red. And now the observation is that there's at most a 1 divided by big N fraction of cells is red in each column. So why is that the case? Well, we can think about the randomized algorithm as first choosing one of these functions ρ of I uniformly at random, and then executing this deterministic algorithm. And then we know this randomized algorithm succeeds with probability at least 1 minus 1 divided by big N. And this then implies that at most a 1 divided by big N fraction of cells is red in each column. Okay. Now what we want to show is that there exists one row which is completely green, because then there exists some fixed algorithm, deterministic algorithm, that succeeds on all input graphs. And that is exactly what we want to show. Okay. note that one row is completely green. This is guaranteed if the number of red cells is less than the number of rows. So this is just an easy application of the pigeonhole principle. And now, as the number of red cells from the previous observation is at most 1 divided by big N times the number of rows times the number of columns, we know that this is satisfied as long as the number of columns is strictly less than big N. Okay. Hence, what we need to do is we need to bound the number of columns, and this is just the number of possible input graphs. Okay, so what are the number of ID labeled N-node graphs? So first, if you only consider unlabeled graphs, then they are at most 2 to the N choose 2, because each of the N choose 2 possible edges can either be present or not. So that's a crude upper bound. And so this is equal to 2 to the order N squared unlabeled N-node graphs. And now we also need to assign each node an ID. And we said we want IDs from an exponential range, so from a range from 1 up to delta to the order of N. And for each node, there are delta to the order N choices, and in total there are N nodes. Hence, there are 2 to the order N squared ways to assign IDs. Therefore, we can choose big N as 2 to the order N squared. And then the resulting probe complexity is little o squared log of big N, and this is just equal to little o of N, as we wanted it. Hence, so what we have shown is now that the randomized LCA with a probe complexity of little o squared log N implies a deterministic LCA with a probe complexity of little o of N. That even works if the IDs are from this exponential range. And then the proof that I have omitted is now if we have this deterministic LCA with probe complexity little o of N, then we can turn it into a deterministic LCA with probe complexity order log star N. And to show this, just as a higher level idea, the idea is that we lie to the algorithm and tell that the size of the graph is only a constant. And then we, to keep this illusion, what we do is that we assign each node an ID from a very small constant range. However, we make sure that if two nodes are very close to each other, then they get a distinct IDs, and then one can show that the algorithm still succeeds. Okay, and now the question is, can we improve this little o squared log N to little o of log N? And the answer is, in general, we are not sure, so I guess it sounds reasonable, but we have no idea how to prove it. However, for the so-called distributed Lovász local lemma, we really can get a stronger bound. Okay, so in the Lovász local lemma, there's by a result of Brandt, it follows that the randomized complexity of the LLL is at least omega log N. And now with the Skeb result that we have shown, we actually get the stronger statement that the randomized complexity of the LLL is omega squared log N. And now what I'm going to sketch is that we can actually improve this bound to omega of log N. Okay, so how can we show omega log N randomized lower bound for the distributed LLL? And the question one needs to ask is, where did this square root log N term come from? And the answer is it came from this union bond over 2 to the order N squared ID labeled N-node graphs, where we once first we upper bounded the number of unlabeled N-node graphs, and then also the number of ways to assign IDs. And now the goal is that we only need to union bond over 2 to the order N many graphs, because if we only need to bond over that many graphs, then we directly get the desired lower bound of omega log N. And so to find this first term, the number of unlabeled N-node graphs, what we do is that we promise that the input is a tree instead of just a constant degree graph. And there are only 2 to the order N non-isomorphic trees, so that's fine. However, we also need to show that the problem is still hard on trees. Okay, and then the question is, what about the ID assignment? And now this is really not so easy to solve, because assume that we don't care about exponential IDs, but even we assign the nodes just a unique ID, just a permutation. Even then there are n factorial, which is equal to 2 to the order N log N many ways to choose a permutation. And this would only result in the lower bound of omega log N over log N. So what we do instead is that we still assign IDs from an exponential range, However, we further restrict which IDs can be neighboring in the input graph. For example, we say that a node with ID 3 can only neighbor with nodes that have ID 1, 4, 20, or 25, just as an example. And with this restriction that we additionally impose, we need to make sure two things. So first is we only want that there are 2 to the order n ways to assign IDs. And the second thing is the problem should not become trivial. And the way how we solve this is with the so-called ID graph, which was also used in a different paper. And here the idea is the following. So each node corresponds to an ID. Hence, we have a graph with exponentially many nodes. And we say that only neighbors in the ID graph can also be neighbors in the input graph. That is only if, let's say, nodes with like IDs 1 and 4 are neighbors in the ID graph, then they can also be neighbors in the input graph, but otherwise not. Moreover, what we ensure is that the ID graph has a constant maximum degree. So think about some polynomial delta. And this ensures the first property, that there are only 2 to the order n ways to assign IDs. Why is that? Well, for the first node, we have 2 to the order n many choices. And then we can assign the other IDs in some DFS way. And each time we only have constantly many choices. And hence we end up with this 2 to the order of n. And then last, we also, this ID graph has a high girth. And it also has a large constant chromatic number. And these properties are important to ensure the second point, that the problem does not become trivial. Okay, so now let me conclude with some open problems. So one interesting question is whether we can get a deterministic lower bound for the distributed Lovász local lemma. So the best known is omega log n, which we just basically proven, which comes from the randomized lower bound. However, we conjecture that there's actually omega of n lower bound. So this would be very nice if one could show this. Even more general question is whether there exists a stronger deterministic gap result. So in particular, we conjecture that there's a gap between omega of log star of n and little o of n. And now if we could show this deterministic gap result, then this would directly imply a deterministic lower bound for LLL of omega of n. And then a more general question is to complete the complexity landscape on constant degree graphs. So what do we mean? So recently it was considered to study this complexity landscape in the so-called volume model, which is very similar to the LCA model. And there one asked which complexities or which pairs of deterministic and randomized complexity are possible. So for which such pair exists an LCL with exactly this complexity landscape. And in this work, what we did, we extended this picture by this very red region. However, on top, you can still see that there are many open questions, whether there exists for particular complexities. And it would be very nice if one could fill these gaps. All right, then thanks a lot for listening to the talk. Bye.